sort of a oxide. And if you look at the densities and compare it to carbides that will most probably form during reduction or synthesis, there is a big difference. So the volume will change. And what this means is that as you form a layer of carbide, the volume will decrease and it will start to crack. And this will, or this might be interpreted that the formation of carbide islands is much more likely than a complete surface. Because if you think of it like if you have mud drying, it cracks and it forms small pieces of mud with valleys in between. And I think this is something that will happen on the surface as well. So a smooth monolayer around a particle, I don't think will happen because of this density difference. What will most probably happen is that you will form cracks and either your whole particle will break apart or you will start to form carbide islands on your oxide particle. Okay, so that was now after reduction, and I hope that I at least put a picture in your mind that we now sit with an oxide particle with carbide islands on it. So there's two regions. You have your carbide islands, non-polar, and your oxide surface, polar surface. Now let's see what we can make of this if we consider CO2 formation during synthesis conditions. Now, I don't want to go, you're probably aware of these two. The primary pathway is where you react your CO with surface oxygen that is directly from CO dissociation. So this does not come from water. It's a direct CO dissociation. Now, what I was trying to do here is to think, if you have this reaction dominating in the formation of your CO2, you most probably will need a high concentration of this and this. If this or this is in a low concentration, it will be a limiting factor and it will inhibit your reaction. So let's see if we just logically think about this, if you can have this and this. If you have this rich environment, then by definition the CO dissociation must be slow, otherwise this will not be high concentration, and this will mean that you will have a low oxygen concentration. So you can either have this or this, not both. The same the other way around. If you have oxygen-rich environment, then the CO dissociation must be fast, and this will mean that this must be low. So just thinking about it, you can either have this or this in a high concentration, not both. So this already puts some doubt if this really is a primary pathway, if this really is the dominating reaction. Look at the secondary pathways, and that's where the oxygen comes from water that dissociates. And this can easily dominate if you have a stable oxide surface with a low dissociation rate, and that's most probably possible. We also did some experiments where we varied the space velocity. Now this, of course, is not completely proof, but it gives us indications. If we lower the space velocity, meaning that we will increase, sorry, I just need to get this right. If we increase the space velocity, we lower the water partial pressure. Also, we lower the conversion. That must be kept in mind. But we then see a lowering in the CO2 formation rate. The other way around as well. If we decrease the space velocity, meaning we increase the water partial pressure, we get an increase in the CO2 formation rate. And that gives us an indication that the CO2 formation rate somehow is influenced by the water partial pressure, giving us an indication that the oxygen must leave the surface as water and then reabsorbs. Otherwise, there will be no real influence on the CO2 formation rate. We also did some experiments where we co-feed water in very small amounts, not to change our partial pressures very much. And we also got the same relationship where we increased the water, we got an increase in the CO2 formation rate. Now, like I said, this is by no means any proof, but at least it fits the picture that the CO2 is from a secondary pathway. And I think this is also generally consensus in the literature as well. Now, what will happen during synthesis regarding the hydrocarbon formation rate? Let's start at the beginning. We have CO. This dissociation will give us this. Sorry, this must be written. I don't think I showed it here. This. It can be this and this, or OH, surface OH species. I don't want to distinguish at this stage between the two because I don't think it's necessary to reach the conclusions. So now, if it is true that we have these two regions, our polar regions and our non-polar regions, in the polar environment, in other words, some sort of an iron oxide rich surface, you will have this and this. This, being polar, will be more stable than this because this is non-polar. This will be more reactive than this. And this will try to leave that surface, and it will be very reactive towards forming your light hydrocarbons and, of course, your oxygenates. It will consume this. Of course, the assumption is that this is more or less evenly distributed between the two surfaces. The other way around, in a non-polar environment, in other words, your carbide-rich environment, you also have this, this, and this, but now the reverse is true. This will be more stable than this because this is non-polar and this is polar. So this will be very reactive and chew up all these surface species to form your water and oxygenates. Now, if you think a little bit about this, in your non-polar environment, your carbide environment, this is normally where we see Fischer-Tropsch happening. And if you look at it, the Fischer-Tropsch reaction kinetically, it's not supposed to form long hydrocarbons. But if you consider this, consuming all this, your hydrogenation rate will be slowed down and your surface species will have a chance to grow. And that might support why we get such long hydrocarbon chains. Okay, so as a general conclusion, I just want to see. Let's consider the FT reaction, putting everything together. The picture that I tried to paint was that we have a carbide surface in small clusters on some sort of an iron bulk. These carbide clusters will give you your FT. Your CO dissociates to form this and this. And as I explained in the previous slide, this will, of course, react further to your CH2 monomer that will propagate your chain growth. These species will be very unhappy in a non-polar environment, and it will be very reactive, consuming a lot of your hydrogen to form water. And this water, of course, is also extremely unhappy in this non-polar environment, and it will quickly leave your surface. Of course, explaining the lower hydrogenation rate and the chain termination and favoring chain growth. Okay, for the water gas shift reaction, the reverse, the picture that I wanted to sketch is that it's happening on an oxide surface, a polar environment. You of course also have your CO dissociation. It will form this and this. Of course, the reverse, this will be much more reactive because of the polarity difference, consuming this, forming your light hydrocarbons. This will also form your light oxygenates. If you also think about it, this polar surface will be much more reactive. You have now your water that left the surface, and if it needs to absorb on the surface, it will, of course, if it has a choice, it will much rather go to the polar surface where it will be much easierly absorbed to dissociate in this and this. That will react with this to form CO2 and hydrogen, giving you a water gas shift reaction. Another consequence of this, and we talked yesterday to Bert a little bit about this, is if you think about the alpha value of our Fischer-Tropsch reaction, we normally see 2 alphas. And this might explain the fact that we see 2 alphas. The 1 alpha up to C5, C10, whatever, C10 rather, can be explained by, if you look at your Fischer-Tropsch reaction, no, sorry, it's in the oxide. This is where you form all your light hydrocarbons. Because of this being so reactive, it will react with this very much faster than this or this, and it will leave as methane or limited chain growth to form, let's say, up to C10 and leaving the surface. So this might also explain the fact that we get much more light hydrocarbons than we expect if we only consider Fischer-Tropsch happening on a carbide surface. I think that's my story. So I would like to hear your views on this. Any questions?
I have one question.
Yes.
Before you get into the chemistry. Your reactor system that you had 2 knockout traps.
Yes.
200 degrees C and whatever the lower temperature was.
Room temperature.
Is that continuous output, gas and liquid?
Yes.
And so you were able to maintain a liquid level in the reactor?
No, it's maybe Johan can I think the setup is exactly the same as yours. It's
Okay,
a
so
standard knockout. We drain once a day.
So yeah, once a day. Okay, I was thinking, oh, you guys have figured out the filtration.
No.
Okay.
I think it's, I don't know exactly know how your system looks like, but I assume it's very much what you have.
Yeah. It was. It just caught my attention that if it was continuous liquid level or liquid out and gas out, that you guys have made major breakthroughs.
Not for the micro reactors, but for our pilot plant reactors, we have a 2-phase situation.
Yeah. Okay.
Where it's a lot easier to control them.
Yes. So now to the chemistry.
I have a question. When you are activating your catalyst, our typical procedure is we will pressurize the reactor with just nitrogen and heat it up to temperature under just nitrogen. And then we begin introducing the syngas mixture of some kind. Do you start at room temperature with syngas, or do you do the same thing? You put nitrogen in first?
Well, inert gas. Exactly the same. Yeah.
Well, I was
We
looking at the amount of methane and CO2 that you were showing. We were showing, what, 5% methane? Very early?
Yes, in the beginning it's actually
That's 12 or something.
Oh, yeah, very high.
much
Yeah,
more larger.
16% or so methane after 4
Yeah.
hours. What kind of space velocity are you using during activation? I just have the feeling it's much higher, that you're getting such high amounts of methane when you started with a completely inert atmosphere.
To answer your first question, we exactly do the same. We put it under pressure using some inert gas, and only when it's at temperature we introduce some gas.
Okay.
Yeah. And we also did some residence time. That's why I actually removed the first 2-3 hours.
Okay.
We also did some residence time experiments, and we found that you basically have complete removal of your gas in about 2 hours.
Your inert gas.
Your inert gas,
charge,
yeah.
Sure. That's what I was asking.
After 2 hours, what you feed in is basically what you're getting out.
Okay. So
So-
that takes you about 2 hours.
Yeah, it's about 2 hours, and your second question.
So what you're seeing there is not an analysis from error in the analysis.
Okay.
That you analyze the feed and the tail, and that is.
Right. Yeah, all you're saying is your first data point is after you've already flushed all the inert gas out.
Yep.
Yeah. So that's why it's also very important for us to keep our whole knockout system as small as possible.
Mhm.
Otherwise, this time will just get
Right.
too large, and we cannot really follow. The analysis that we're using here is actually very interesting. I don't know if Matthijs told you about it. We're actually in a position now where we can continuously analyze every 20 minutes. We can do a tail gas analysis. So every 20 minutes, we can see what the conversion is, how much of the CO was converted to whatever product, allowing us, in the past, we basically had a point here and a point when we start. We didn't know what happened in between. If we wanted to know, we basically had to manually, every hour or whatever, do these analysis. And what we found, what we do is we do a tail gas and a fresh feed. Now, if you take a fresh feed sample, send it to a GC, you bugger up what you send to the thing, so it will be a little bit skewed. But what we do here is we basically just take a tail gas that's anyway leaving your reactors, you don't interfere with your system, and you basically do your fresh feed there and there, and that will give you a very good indication of what your conversion and your formation rate or whatever is at every half an hour, every 20 minutes.
Now,
So, yeah.
the CO2, if I remember, was about 75%, so
Yeah.
you're getting essentially 100% conversion initially.
Now, this is expressed of the CO that was consumed. So only the CO that was consumed is represented here. So of the CO that was consumed, 70% of it went to CO2, and the remaining 20 whatever percent went to methane, and I assume maybe analysis error or small amounts of FT.
No. But what would be the CO conversion?
Very low. I actually don't know it off heart, but it's very low. At this stage, it's very low. We get very little FT for CO consumption. But that CO that is consumed, almost all of it goes to CO2 and methane.
And are you typically running your reduction or activation phase out like 16 hours or something? Is that
Yeah,
is
that's
that your
16
normal?
hours. I think it's a universal truth. That's normally from 4 o'clock in the afternoon till 8 o'clock in the morning.
For some people.
It was a universal truth, but it's not. When we started to look at activation, we are busy with a big project for the China plant, and it was clearly stated from the engineering side that if we want to use only one reactor for the activation of the catalyst, we need a maximum of 16 hours.
Mhm.
So we did a whole range of experiments to look at how fast can we do activation and how high activation can we get. And we clearly had the point of it must be faster than 16 hours. So this is just not overnight.
Yeah, well, I mean, it looks like the bulk of it's done at 6-7 hours, something like that.
Yeah, what you actually have to look at is your FT, right? When that levels off, it's basically, you can say that it's fair chance that it's but not necessarily.
This is what you see there is the change on the surface, but there's still a continuous activation or a generation of more and more carbide. so that your FT rate will go up, and only after about 16 hours it starts off.
I mean, an interesting consequence is, I'm just going to play devil's advocate here, is if, for instance, your FT levels off after, let's say, 10 hours, and you stop it there, and all of a sudden your catalyst dies now, you can argue, okay, that leveling off of FT might not be your activation. It's just, you know, a consequence. But what you need to make is, let's say, a critical amount of carbides, and that only happens after 16 hours. So yeah, it's a difficult thing to see or to propose that you're actually finished with activation by looking at any one graph. You basically have to combine everything and have a good understanding of what you're doing during activation to get a stable and active catalyst. You need to say, okay, at this point I'm finished. So Methane is right. We not necessarily do all our activations for 16 hours, but at this stage, you know, it's overnight, it's easy, and it's not necessarily optimal.
I don't know if you caught Bell's talk. He gave a plenary lecture in the morning, and he was talking, part of his talk about related CO hydrogenation catalysts, methanol.
Yes.
Right? And if you look over like a wide range of methanol synthesis catalysts, they're also the same catalysts that are really, really good for water gas shift. And in his mechanism that he's proposing, he has basically formate being hydrogenated as the intermediate for methanol synthesis. And it's also been proposed quite often that formate is intermediate to water gas shift. And basically in those systems you have a metallic function and you have like a partially reducible oxide function. And now if we move to iron, I'm just thinking that now if you go in the literature and you look where people have put gold on iron catalysts, Fe2O3, they're actually making very, very good water gas shift catalysts with these systems. And in some cases are proposing formate is an intermediate there. And I'm just wondering if, now you're proposing a redox mechanism here basically for the iron component, but that usually is proposed for high temperature shift, right? Now you're at low temperature pretty much. So I'm wondering if maybe there might be a formate intermediate there that might be available.
Well, I don't want to stick my neck out too far and say that it's a formate or whatever intermediate.
Yeah.
But I think what I can take from that is, I also read a lot of these CO oxidation papers, basically the water gas shift catalyst. And what the general consensus there was that you basically need some oxygen layer on the surface for it to be active. And that's a polar environment. So I think that was the thing that I took away from that. Not necessarily what the intermediates was, but how the surface should look like. And I think the fact that it was a requirement that in almost, or many of the cases, you need a polar surface for the water gas shift reaction to proceed.
Well, my understanding is that you need both. That you need the synergy between the metal and the oxide so that you can dissociate the water on the defects on the oxide to make maybe OH groups or whatever.
Yeah.
And then the CO reacts there on the oxide to make the formate, and the metal helps to dehydrogenate that during the water gas shift. And then basically during methanol synthesis, they're saying that you get the formate on the oxide, and then the metal is there to help transfer hydrogen to hydrogenate the formate to the methanol. So you get, essentially, it's at the interface with these things.
Personally, I also like the idea of a formate intermediate because, I mean, chemically it makes sense. So, but I'm not there yet.
Yeah.
It's something that I'm going to try to fit into this picture, and building it out further. This is only a start, and that's what I would like to discuss with as many people as possible, because everybody is bringing something new to the table, and changing the way that you think. But the format intermediate is definitely, I like the idea of a format intermediate, and it makes sense. So I'd like to see if it fits the results that we're getting, the experimental, the selectivity work that we're going to do, the kinetics that we're going to do. I'm going to try to see if it fits, and if it fits, another thing that I also just want to make, and I think I don't want to say that this is a universal truth, but certainly in our case, it fits most of the data. Now, saying that, I don't necessarily want to stick my neck out and say that, like for instance, in your catalyst case, that it's also the truth, because I mean, you're making 80, 90, 100% carbides. And only during synthesis, I think you go to 60% or 70%?
That's about 40% carbide,
40%,
60%.
And I mean, in our case, we work with a much lower carbide content. So, yeah, I think it's process specific, and of course also to a certain extent catalyst specific. Depends on what you have in your catalyst. But for our case, I think it's.
What happens to the relative rates of FT and water gas shift when you start adding steam?
Yeah, the water addition, I can't remember offhand what happens to the FT rate.
What we normally see when we add water is that we start to change the relative rates of FT to water gas shift. Water gas shift is going up, FT is going down, but that's irreversible. As soon as you increase the water gas shift rate, it never comes down. I think it's not exactly the same as what you see on the surface. When you add water, the water gas shift rate goes up, but if you remove the water, it comes down. What we see is that as soon as there's too high water partial pressure, we damage the catalyst surface, and the water gas shift rate is not coming down after that. You can maybe manipulate it a little bit with the water partial pressure, but the water gas shift rate keeps on going up with time. It's never coming down.
For the space velocity variations, it was basically the same. And the one thing that we do know is that CO and hydrogen partial pressures influences your FT rate much more than it does your water gas shift rate. And temperature, on the other hand, influences your water gas shift rate much more than it influences your FT. So you have to be careful, when you play around with these, because those two will also, of course, change the ratio of your FT to water gas shift.
You must remember that I think the way we do Fischer Tropsch in Sasol is a little bit different from what you try to do. We are using a low gasifier, which will give us a very high hydrogen to CO ratio, and you are using a gas from a shell gasifier, which is a low hydrogen to CO ratio. So if you want to do Fischer Tropsch, you need hydrogen. If we want to do Fischer Tropsch, we don't want CO2. So our catalyst is designed not to make CO2. Your catalyst is designed to make CO2. So I think that's a big difference in the two systems. We want the CO2 selectivity as low as possible. Otherwise, we will end up with pure hydrogen in the tail gas and no Fischer Tropsch.
Yes, my question is also regarding the FTH reaction and water gas shift reaction. As you mentioned, CO2 is formed by adsorbed oxygen and adsorbed carbon monoxide. Because the adsorbed oxygen comes from the oxide, iron oxide, as you suggested, polar material. Do you think the water gas shift reaction will depend on totally on the Fischer-Tropsch synthesized reaction? Because the oxygen in the adsorbed oxygen comes from the dissociation of the CO on the iron carbide. Do you think the water gas shift reaction relies on the Fischer-Tropsch synthesis reaction? Have you?
So I didn't quite get the last sentence. You asked if the water gas shift reaction depend on the.
Can you go to the mechanism of the CO2 formation?
During reduction or synthesis? Synthesis.
This is
This one.
look at the second category.
This one.
Yes, the CO2 formed by adsorbed oxygen, where adsorbed oxygen comes from the CO dissociation, which taking place on the iron oxide, iron carbide.
Of course, yes.
So, in this case, the water gas shift reaction must be rely on the FTS rate.
I think if I understand you correctly, what I'm saying is that the dominant pathway is this one, and that surface oxygen does not come from where is that reaction? The dissociation of CO. This oxygen comes from the oxygen after the after this reacts further to form water. So you basically first form water, and that leaves the surface, and that needs to reabsorb. There.
In CO2 formation mechanism, during the reduction is different from the CO2 formation during the physical reaction.
Yes. In the beginning, and I think that's why almost all of your CO that gets converted is going to CO2. Because you don't have any FT in the beginning. So the water formation, there's no water that forms because your FT is almost non-existent. So the CO2 will be dominated by this reaction. Whereas, or the oxygen can come from your oxide surface as well. Whereas during synthesis, this is your dominant CO2 formation, yes.
Also, during the reduction, we find moments in CO2 concentration parallel P. At the beginning, it's lower than reach peak and decrease. But I saw your CO2 concentration just decreasing. At the very beginning, it's very high.
Yeah.
And it decreased to level.
So you basically,
See, the first peak is due to like hematite to magnetite, and that is very sharp and very quick. So unless you have a very low time interval, it's very difficult to monitor that peak. So they had a like 4 hours gap.
yes, so you basically say that what you're seeing is that you get a peak here and then it goes down.
That means
Yeah, maybe we see it as well, but I mean, like I said, our residence time in the reactor is what, 2-3 hours. So I really don't want to say what happens before. I think that's 4 hours. So I will put a question mark on what we see during the first 4 hours.
So you guys did not do any analysis in that 4 hours.
Well, we do, but I mean, we get it, but I mean,
You're so
don't
dilute with
pay
nitrogen.
attention.
You can't tell
Yeah.
it's
thank you.
I have questions
Yes.
regarding the iron. potassium catalyst. So you say his catalyst has more favor to the CO dissociation than the hydrogen.
What I'm considering there is, that's the copper. What I'm considering is that we basically add potassium and copper to our catalyst, and that's normally very well dispersed. So what I'm considering is, in the region where you have species like this will happen. In the region where you have iron copper, that will happen. So as a bulk, all of this will happen.
Is homogeneous catalyst or what is it? Potassium just promoter.
Potassium, the copper is promotion. But the way that we add it normally leads to a very well dispersed potassium and copper into the iron. Of course you get islands, but this normally exists, and same for the copper as well. Yes?
Is that an alarm or is it
After your say after your 16-hour first activation, I was just wondering, trying to imagine your model that you have these islands on the surface of your grains.
Yes.
You have the carbide islands, and then in between you assume you still have an oxide phase, right?
Yes.
And do you have any idea how what the thickness is of the actual outer layer that has these islands on it? And if so, I mean, the thickness would very strongly determine how fast you can have overgrowth and healing in between the cracks.
Yeah.
And what really controls that and how fast that goes, I would imagine, would really be determined by the original size of the particles that you start out with, right? And when we look at aged catalyst that had very small particle size, let's say in the nano size, 5 to 10 meter, we find usually a very nice homogeneous layer of carbide. And there may be on the outside some oxide phases, but it's usually a pretty good homogeneous rim, so there must have been some either healing in between the cracks and overgrowth. And how fast that happens, I was just wondering if you have any idea on that? And how that controls, like you want to see both phases, the polar and non-polar, side by side or alternately. But how fast these heal and overgrow would determine in the end what the selectivity is.
At this stage, I'm leaning towards, under certain conditions, of course, that there is interconversion between the two. And I think all that I really can say about the size of these islands is that they are very small. It's not like you have a big blob of carbide sitting on a big blob of oxide. I think you have the bulk of your oxide and then very small islands of carbides. That's maybe too small for us to detect as single entities, and we might get the impression that it's
we call it nanozones or something.
Yes.
The entire zone
Yeah.
that's on the outside of the grain.
Yes.
But I was thinking, the smaller your particle is that you start out with, the faster you might be able to heal that, because then your surface area relatively changes with respect to the bulk.
Yeah. What I'm also considering at this stage is that maybe there's a dependence on the actual surface of your carbide and your chain growth. Because if you have CO dissociating in the middle of a big island, your oxygen will leave immediately, but that carbon that's left behind in the region where there's a fair amount of hydrogen is in the perimeter, where you actually have the interface between your carbide and your oxide. So for that to move or get closer to the edge, I think that's where most of your hydrogenation takes place, and that's where you leave. But of course, that's just a speculation at this stage. Yeah. So, and that's one thing that I would also like to investigate is if there's actually a size dependence on, the surface of your carbide relative to what your, let's call it, alpha value is. what I also would want to do is to try to separate these two alpha values mathematically and see if it makes sense if I correlate, of course, your size and your water gas shift rate. And there's a couple of things that you can do to get indications if this is right or not. And of course, like I said, we're just starting with this, and this might change. In a year's time, I might come here and present that it's one side. But at this stage, this seemed to make sense.
You have two different environments evolving, which you're saying there.
Yeah.
You have iron carbide and iron oxide, and you make changes in partial pressure, and you change the relative amounts of these phases. Do you really have two sites, or is it really one site since it's still iron?
Yes, it's something that we have to be very, very, very careful about. You know, jumping to conclusions by changing 17 different parameters. But you know, what?
I mean, you could claim that it's two sites or one site. You can make a case for either. Right?
Yes, I think if you have to, of course, when you do indirect if you use indirect evidence to reach conclusions, you have to have as many as possible. And this is after only a few. And of course, we will start to add indirect indications. And the more that we add, you know, the higher possibility it will become that it really is like that. And at the end of the day, I mean, we also look at it slightly different than people in academic environment. In the end, we want to manipulate this catalyst to, let's say, produce as much wax as possible. And if the model works to predict, that's all we need. So we're gonna try to firm up this picture up to a point where we can use it.
Like the kind one.
Yes. It will be interesting to go further and really try to I wouldn't say prove, but you know, to get a very strong indication as far as we can go. But I mean, if we are at the point where we can manipulate our catalyst using this model, it's in the end what we want.
Do you think iron carbide and iron oxide transform each other during the Fischer reaction?
Yes, like I told her, I'm leaning towards that you can change your because you have an interface, and the carbide can go to the oxide, and the oxide of course can grow into your carbide, and that will very much depend on your reaction conditions, how much water you give your catalyst, parameters like that. So at this stage, I'm leaning towards that it can actually interconvert, and that might be one of the deactivation mechanisms as well. Because of course, if you have your oxide surface that's too big, and you don't, I'm going to use very loose terms now, but if you don't let your oxide surface work to give you water gas shift, you know, all that activated oxygen might sit around there and do some other things, and you might get crystal growth in that region, and you might form hematite, magnetite, getting your crystal to grow. Irreversible. So yes, you can interconvert them, but I think there's a cutoff point that if you give, for instance, too much oxidizing environment, you might just push it too far, and it might form some stable crystal, some stable oxide that the rate of going back is just too small.
On the potassium promotion there, is that basically you're saying there's an electronic effect, so the potassium helps promote the dissociation of CO?
Yes.
But you're not saying there that the CO dissociation rate is faster than the hydrogen dissociation rate, or you're just saying that you're getting more faster CO dissociation relative to the undoped iron?
I think what I tried to picture here is that this is much faster than this. So in these environments, you will have a high concentration of this and this, because there's no hydrogen or the concentration of this is too low for all of this to be consumed as water or going to your CH2 and forming your FT. So these things will lie around there and will have nothing to do. And what I'm trying to picture here is that normally at these higher temperatures, these things might migrate, and you might get a segregation. And you might get, like oil and water. They will cluster together. I can call it that. Yes.
I'm not sure how to picture it, but would you expect to see a difference then with supported versus non-supported iron catalyst if you use something like a silica support? Again, looking at the polar, non-polar surfaces, would you then expect any contribution then from the support as well to help, to decide how many of these carbide clusters you have? Would there be any expectation with your model to?
It will be difficult to say, but I would say if you have iron, copper, potassium that's similar in particle size with silica as well, or whatever support, I think this should work as well, or this should explain work. This should explain as well.
The reason I'm thinking about that is because if you use carbon nanotubes as a support, there's supposed to be some very high stability for doing FT reaction. And I'm trying to see if that, like your model would help explain some of that stability, which we don't know now why these are so stable. But if that model might help explain.
I think what you might have to keep in mind when you go to supported catalyst is maybe your crystallite size. It might become too small to really say that it's the same effect here, because these crystallite size are, I would assume, a lot bigger than that on a support. So yeah, it might explain, but I think you have to be careful when you go to too small crystallite size. But I don't know.
I guess they've gotten tired of